Welcome back to the course of chemical crystallography. In the previous lecture, we discussed about the atomic packing factors, calculation of cation to anion radius ratios, and we discussed about various interstitials. So, we would like to continue in the same line, and we would like to see some of the well-known crystal structures which are important to understand the packing and the corresponding atomic arrangements. Here we are having a ceramic crystal structure of the type AX crystal structure, where you have equal number of cations and anions. The most common example is the rock salt structure or the NaCl crystal structure of sodium chloride. In this case, the radius ratio lies between 0.41 to 0.723. So, it means the coordination is 6:6 coordination. So, what we see here is that the sodium cations, Na plus cations, occupies the octahedral sites and chloride ions occupies the corners and face centered sides of a face centered cubic lattice. So, it is a 6:6 coordination, that means it is 6 coordination with respect to both sodium and chloride, and this structure is represented as interpenetrating face centered lattice. So, what does it mean? See, here what I have drawn is a chloride lattice which is corresponding to these red circles at 8 corners and 6 faces of this unit cell. And then I have one slightly offset, which is actually offset by half unit along one direction, a lattice of Na plus ions represented in blue. Again, it is a face centered lattice with 8 corner atoms and 6 face centered atoms. So, now if we try to merge these two in this way, what you see is that the two face centered lattices are penetrated with each other. So, two face centered lattices, when they interpenetrate, we call it as interpenetrating face centered lattice. So, the next type that we would like to discuss is the AX type of crystal structure, where again we have equal number of cations and anions, generally named as a rock salt structure, when we have the radius ratio very close to 1. As we have seen in the previous lecture, that when the radius ratio approaches 1, we get coordination number 8. That means cations are large enough to prevent the anions from contacting each other, or they are not in touch. So, the unit cell contains cesium plus and 8 Cl minus anions, each contributing 1/8 through the unit cell. So, what we have is cesium atoms at 8 corners, chloride atoms at 8 corners, and cesium atom at the center of the unit cell. So, this is, remember, this is not a body centered lattice, because the body centered atom here is not same as the corner atoms. So, it is actually a simple cubic lattice of chloride ions and a simple cubic lattice of cesium ions, and they are then interpenetrated just like the sodium chloride interpenetrating face centered lattice. Now, let us see what is zinc blende structure or ZNS structure. In case of zinc blende structure, the radius ratio is 0.44. So, ideally it should have been that the octahedral sites are occupied by the cations, but in reality the tetrahedral sites are occupied by the cations. So, now if the sulfides adopt the hexagonal close pack structure, then the structure of zinc sulfide is called as Wurtzite structure. If the sulfide ions originally adopt a face centered lattice, then this particular zinc sulfide structure, crystal structure, is called the zinc blende structure. So, in this case, the sulfide ions are in the cubic close pack arrangement, that is FCC. So if you look at the figure on the left, you have sulfide atoms occupying the 8 corners and 6 faces, and then the zinc ions are occupying the alternate tetrahedral sites inside the unit cell. So this indicates that for one unit cell you have 1, 2, 3, 4 zinc ions which are fully occupied, and then you have 8 sulfide ions and 6 sulfide ions at faces, which means there are total number of sulfide ions is 4. So again it is 1:1 coordination, 1:1 formula unit zinc sulfide, but in case here the alternate tetrahedral sites are occupied. So now let us see the crystal structure of a fluorite structure, calcium fluoride, where the radius ratio is about 1, very close to 1, 0.929. That means 2 ions are essentially of same size. So here what we have on the left hand side is that the fluoride anions are represented as red circles and the calcium cations are represented as blue circles, and what we see is that we have a simple cubic lattice of fluoride ions, and at the center of that simple cubic lattice we have a calcium ion present. But if you look at the corresponding adjacent unit cell, the fluoride ions are forming a simple cubic lattice, but the center is vacant. The same is true for the lower part also. That means the simple cubic arrangement, which is filled with 50% cubic sites, are filled in this case of calcium fluoride. So coordination number for calcium is 8 and coordination number for fluoride is 4. Let us see the same in a different arrangement. What does here the fluoride ions lie in the cubic arrangement. The insertion of calcium ions into the cubic holes causes the structure to expand so that the fluoride ions are not in contact with each other. In fluorite, half of the cubic holes contain a calcium ion and the other half is empty. So this is the structure that we are discussing, where we have calcium represented as gray spheres. The calciums are now represented to form a face-centered lattice, because you have 8 corner atoms sites occupied by calcium, 6 face centers occupied by calcium. So it is a face-centered lattice of calcium, and then every tetrahedral interstitial is occupied by fluoride ions. If you remember the zinc blende structure, where we had sulfide ions at all the face center positions, that means 8 corners and 8 face center positions, and we had zinc ion at every alternate tetrahedral holes. Here the fluoride ion occupies all the possible tetrahedral holes and forms this calcium fluoride structure. So the fluoride structure can also be seen as calcium ions in the face centered arrangement and fluoride ions occupying the tetrahedral sites. So fluoride has a 8:4 coordination geometry. So now the last type of structure that we wanted to discuss is a spinel structure. Spinel structures have a general formula of AB2O4. An example of spinel is MgAl2O4. So here we see that the cation A is divalent and cation B is a trivalent cation. So in this case, what we have is slightly complicated. You see, the structure consists of a cubic close packed array of 32 oxide ions, which forms 64 tetrahedral holes and 32 octahedral holes in one unit cell containing 8 formula units. That is, this is the formula unit which we are talking about. 8 such formula unit is present in one unit cell. So, in this large unit cell, there are two types of subcells. You have two structures A and B. In case of structure A, we have two tetrahedral sites within 1/8 of the unit cell is occupied. So, the oxygens are occupying the face centered lattice positions in this 1/8 of structure, and then inside you have two cations present in that. So, here two kinds of occupied tetrahedral sites in spinel subcell A. So, the atom A or the cation A is represented as green. So, this is the cation A. In the structure B, it shows a filled octahedral site, which is this one. So, this is the cation of type B. That means a trivalent cation is sitting at that particular subcell of this face centered cubic structure. So, here the second subcell also has face centered cubic lattice of oxide ions, and the center is occupied by a trivalent cation. So, this particular arrangement is then stacked in a three-dimensional lattice. So, if on the right hand side, if we identify the different subcells as A, B, A, B, B, A, B. So, this corresponds to the unit cell of a spinel structure corresponding to eight formula units per unit cell. So, to summarize this, we have a set of ceramic crystal structures with different coordination numbers. We have seen when it is named as rock salt structure, the structure has a type AX, that is the common formula AX. Anions are packed in face centered lattice. The cation and anion both have coordination 6:6, and there are examples like sodium chloride, magnesium chloride, they occupy these rock salt structures. A cesium chloride structure is also of type AX, but you see this is simple cubic, as I already indicated that it is interpenetrating simple cubic lattice having 8:8 coordination for both cation and anion. So, a cesium chloride structure is interpenetrating simple cubic lattice with 8:8 coordination. The next type that we discussed is a zinc blende structure, where the formula is again AX, that is the stoichiometric formula, but this is a face centered cubic lattice where the coordination number is 4:4, that means anions are occupied in face centered lattice, cations are located at the interstitials, the tetrahedral interstitials. So, these are the examples are zinc sulfide, silicon carbide, etc. The next type that we have seen is a fluorite structure. It is having a general formula AX2. This is again a simple cubic structure with 8:4 coordination, and calcium fluoride and uranium oxide are two examples of such structure. We have not discussed about perovskites, which I would like you to read yourself. The formula is like ABX3. We have two types of atoms just like spinels. It occupies a face-centered cubic system where the coordination number of cation is 12 for the cation A and coordination number 6 is for cation B, and the anion is always a 6 coordinated. Example is barium titanate. And we discussed about the spinel structures where you have a B2X4 kind of molecular formula or the stoichiometric formula. It again occupies FCC, where the cation A, which is a divalent cation which has coordination number 4, a trivalent cation B occupies octahedral sites with coordination number 6. The anion has coordination number 4, and example is MgAl2O3. So with this we would like to conclude this lecture on ceramics and ceramic structures and their coordination numbers, radius ratios, etc. I would like to request all of you to go through a standard textbook to understand this.